In this video, we're going to be doing some exercises that help reinforce the ideas that we learned in the last video on probability models. That was the really long video. Well, I know that you had a lot to absorb, so hopefully this is going to help kind of make things more concrete for you. So, let's just charge right in. Example 1. We have a new gimmick has 30% of Skittles candies covered with speckles. These groovy candies are mixed randomly with the normal candies as they are put into the bags for distribution and sale. You buy a bag and remove candies one at a time looking for speckles. So, question 1. Each time you remove a candy, is this a Bernoulli random variable? And the answer is yes. This is a perfect example of a Bernoulli random variable. Why? Well, what are the three characteristics? Number 1, there are only two outcomes. Speckles, no speckles. Okay? Speckles, success. No speckles, failure. Alright, there's a constant probability, 30% of success each time. And each trial is independent. Now, those last two conditions, you may be saying, well, actually, the probability of success changes each time because I removed one from the total population, which also means that they're not completely independent. Yeah, well, remember our condition that as long as our sample size is smaller than 10% of the whole population, that really doesn't become an issue? That's the case here. One bag of Skittles compared to all the Skittles in the world, way less than 10%. So we're safe here. Okay, so we have Bernoulli trials, which means I'll bet you we're going to use either a geometric distribution or a binomial distribution. So, what is the probability that the first speckled one we see is the fourth candy we get? Okay, whenever we talk about the first one that we see, or how many trials it takes to get one, that means we have a geometric random variable. Okay? X is geometric with a probability of 0.3 for success. Okay? And so that means the probability that X equals 4, the fourth candy that we get, is going to be the probability of failure, 0.7, to the third power, times the probability of success. And that's going to be 0.1029. Okay? So there's about a 10% chance that the very first speckled one we see will be the fourth candy that we get. Okay? What's the probability that the first speckled one is the 10th one? Well, use the same idea. The probability that X equals 10 is going to be the probability of failure. That's 9 failures. That's to the 9th power. Times the probability of success on the 10th one. Okay? And that's going to be 0.012. Okay? Approximately. So there's only a 1% chance that the first speckled one we see will be the 10th one we pull out. Now, what's the general formula? The general formula, or the PDF, is P of X equals 0.7 to the X minus 1 times 0.3 to the 1 power. And that's it. Because if you remember, the general formula for geometric distributions is it's Q to the X minus 1 times P. Well, there's Q, there's P. Alright? Now, how many do we have to expect to check on average to find a speckled one? Well, that's going to be, remember what the mean of a geometric random variable is? It's 1 over P. So that's going to be 1 over 0.3, or about 3 1/3. Actually, not about 3 1/3, exactly 3 1/3. Okay? So we would imagine that if we go through this process over and over and over, that on average, we would have to check 3.5 Skittles in order to find one. Okay? Now, the final question says, what is the probability? Let me just scoot this up. What is the probability that we'll find 2 speckled ones in a handful of 5 candies? Now, this is different. This time, we're not talking about how many we have to pull out to find a speckled one. This time we know how many we've taken. 5. And we want to know, well, what's the probability that we'll get 2 successes when we've done 5 trials? This is no longer geometric. Now we have a binomial random variable. Okay? It's a binomial random variable where n is 5 and p is 2. Oh, what am I talking about? And p is 0.3. Okay? It's the probability of success. And what we want to know is, what's the probability that x equals 2? Okay? Well, the formula that we have says, well, this is going to be 5 choose 2 times p, 0.3, to the second power, because we have 2 successes, times 0.7 to the third power, because that's going to be 5 minus 2. That's the number of failures that we got. And that turns out to be 0.3087. Okay? And in case you've forgotten how to find 5 choose 2, you just take out your TI-84, or a TI-83 will also do. And what we do is we hit 5, and then we go to Math, arrow over to Probability, choose NCR, and then 2. And that tells us it's 10. Okay? So 10 times 0.3 to the second power times 0.7 to the third power gets us 0.3087, and that's what we were looking for. Okay? That's the hard way. Let's do it the dirty, rotten, cheater, stinking, easy way. Okay? And the easy way is to say second distribution, and I'm going to go down to the binomial PDF. There it is, binomial PDF, and I'm going to say binomial PDF 5, 0.3, 2. Okay? This is the probability out of 5 trials and a 0.3 success of each trial that I will have 2 successes. Enter. Hey, look at that. Exactly the same answer. 0.3087. Alright. Next problem. We leave our Skittles behind, and now we have to talk about jumper cables. Okay? So, 40% of the students who drive to school carry jumper cables in their car. That's very responsible of them. Your car has a dead battery, and you don't have jumper cables. Not so responsible for you. So you decide to stop students who are headed to the parking lot and ask them if they have a pair. Is this a Bernoulli random variable? Well, I would say yes. Okay? This is a big school. And I'm pretty sure that the number of students I stop, my sample, is going to be smaller than 10% of all the people that are here at the school. So I'm fairly sure that that's okay. So that means I can assume independence. They have jumper cables. They don't have jumper cables. Success, failure. So that's 2 options. And there's a 40% chance. It stays at 40% because each time I grab somebody, that's really not reducing the percentage enough to really matter that much. Okay? So what is the probability that the third student you ask will be the first one to have jumper cables? Whenever we're talking about the first one, that means we have a geometric random variable. X is geometric with probability of 0.4 of success. And the probability that x equals 3 is going to be 0.6 squared times 0.4, which is, do that in my head, 0.144. Okay? So there's a 14.4 chance that the first person I ask is going to be the third person, that the first person with jumper cables will be the third student that I ask. What's the probability that the first student I ask will have jumper cables? Well, one way to do this is to say, well, the probability that x equals 1 is going to be 0.6 to the 0 power times 0.4, which is just 0.4. Or I can think to myself, look, 40% of the students who drive to school carry jumper cables. What's the probability that the first person I ask is going to have jumper cables? 40%. It's kind of self-explanatory. Now, what's the probability that 3 or fewer students must be stopped to find cables. Okay? Well, this is the probability that x is less than or equal to 3, which is going to be the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. Okay? Probability that x equals 1, I already calculated that. That's 0.4. Probability that x equals 2 is going to be 0.6 times 0.4. That's 0.24. Probability that x equals 3, I already calculated that. That's 0.144. And when I add all these up, I get 0.784. Okay? So there's a 78.4% chance that I'm only going to have to stop 3 or fewer students to get my cables. Okay? Now, let's assume for a second that you are just really lazy. Okay? Well, I've got good news. You hit second distribution, go all the way down to the bottom, and you'll see geometric CDF. And what you do is you choose geometric CDF and you say my probability is 0.6. I'm sorry, that's not true. My probability is 0.4 of success. And I want to know what's the probability of getting 3 or fewer. And 0.784. Sure enough, that's the right answer. Okay? Now notice, I use geometric CDF, not geometric PDF. This is the cumulative density function. So that gives me the probability of getting 3 or fewer. If I use the geometric PDF, I would get exactly 3. But really, geometric PDF, I really don't think that's worth it. It's pretty easy just to do q to the x minus 1 power times p. Okay, and then finally, what's the average number of students that I'm going to have to stop to find jumper cables? Remember what the average number of students is in a geometric random variable? It's going to be 1 over p. So this is going to be 1 over 0.4, and that is 2.5. So if this happens to me over and over and over again, the average number of students I'll have to stop will be 2.5 students until I finally get a clue and go out and get a new battery for my car. Okay, last example we have is blood donors. People with O negative blood are called universal donors because O negative blood can be given to anyone else, regardless of the recipient's blood type. Unfortunately, only about 6% of people have O negative blood. So, if donors line up at random for a blood drive, how many do you expect to examine before you find someone who has O negative blood? Okay, first of all, I don't care how big your blood drive is, there's no way it's 10% of the Earth's population. So, I think we can be safe that this is these are Bernoulli trials. Okay? It's going to be my, either they have O negative blood or they don't have O negative blood. So that's success or failure. We're less than 10% of the population, so we can assume that these are independent trials. And 6% is our success ratio every single time. So these are definitely Bernoulli trials. So, if donors line up at random for a blood drive, how many do you expect to examine before you find someone, also known as the first one, who has O negative blood? That's going to be a geometric random variable with a success ratio of 0.06. And what we would expect to do is, what we would need to do is find the expected value of x. And that's going to be 1 over 0.06, also known as 16 2/3. Okay? Don't get confused and think it's 0.6. This is 6%, which is 0.06. So what's the probability that the first O negative donor found is one of the first 4 people in line? Okay? Well, this is the probability that x is less than or equal to 4 when x is a geometric random variable. And, oh shoot, I'm feeling lazy again. Let me just do this again. I'm going to do second enter to pull up that geometric CDF again. So this time, my success probability is 0.06. And I want to know what's the probability of getting 4 or fewer. And it's going to be 21 0.9%. So that's going to be 0.219. Okay? Now, let's stop for a second and just think. What's the probability that the first O-negative donor found is one of the first 4 people in line? Well, let me ask you a question. What's the probability that the opposite is true? What's the opposite? What's the complement of that? The complement of the first O-negative donor being one of the first 4 people in line is the first O-negative donor being 5th or later. All that means is none of the first 4 people have O-negative blood. Well, that just means the first person doesn't, and the second person doesn't, and the third person doesn't, and the fourth person doesn't, and these are all independent random variables. And so that means another way of doing this would be to say this is 1 minus 0.94 to the 4th power. And if I take 1 minus 0.94 to the 4th power, I get exactly the same number that I did before. Okay? 0.94 to the 4th power is simply the probability that none of the first 4 people in line have O-negative blood. Okay? So, what's the probability that there are 4 O-negative donors in a group of 50 donors standing in line? Well, now I know exactly how many people are here. This is no longer geometric. This is a binomial random variable. And n is 50. The probability of success is 0.06. And I want to know what's the probability that x equals 4. So again, let me grab my best friend, and I'm going to say second distribution. I'm going to go down to binomial PDF, because I want to know the probability that x equals 4. Okay? Not that x is at 4 or less, but that x equals 4. So binomial PDF, I'm going to say 50, 0.06, 4. Oops. Okay? Can you see that? So binomial PDF, 50, 0.06, 4, and I get the answer 0.173. So this is 0.173. It's a 17.3% chance that I've got exactly 4 O-negative donors in a group of 50 donors. Okay? Now, one might have read that as at least 4 O-negative donors, and if that's the case, then I would have to find the probability that there's 3 or fewer using the binomial CDF, and then do 1 minus that. Okay? Moving on. What is the probability that 7 out of the 100 donors that donated blood last Wednesday were O-negative? Okay? N is 100, 7 is x, so this is going to be x is binomial, n is 100, and 0.06 is my probability of success, and the probability that x equals 7 is binomial PDF. I'm just going to hit the second enter again. Binomial PDF, where n is 100, p is 0.06, and I want to know probability of getting 7 people, and it's 14.2%. So 0.142. Okay? Pretty straightforward. E. What is the probability that 10 or fewer donors out of an 87 donor pool are O-negative? Okay, N is now 87. And now, so X is binomial, where N is 87, P is still 06, and now I want the probability that X is less than or equal to 10. I'm going to use a binomial CDF, the cumulative density function. Okay? So go to second distribution, down to binomial, whoa, there it is, binomial CDF. And I say, I've got 87 people, a 0.06 chance of success, and I want to know the probability of having 10 or fewer, and I get, whoa, pretty high probability, 98.5%. So 0.985. Let's just think about that for a second. Okay, there's only a 6% chance. I would expect out of 100 people to have 6 O-negative people. And this is saying 10 or fewer, which covers 6 and everything less than it. And there's 87, less than 100 people. So yeah, it makes sense that this is going to be a very high probability. Okay, what is the probability that 4 or 5 of the donors out of a group of 63 donors are O-negative? Well, okay, X is now binomial with N equaling 63. P is still 0.06. And I want to know the probability that either X is 4 or X is 5. Well, that's just going to be the probability that X is 4 plus the probability that X is 5. So let me go to my binomial PDF. Let me pull this down so we can see a little better. So second distribution down to binomial PDF. And I'm going to do 63, comma 0.06, comma 4. And I get pretty much 0.2. Then I'm going to add that to binomial PDF. 63, comma 0.06, comma 5. And I get 0.35. So 0.352. So slightly over a third. Okay. What's the probability that at least 1 out of 20 donors is type O negative? Okay, this is an easy one, okay? Now I could say the probability that X is greater than or equal to 1 equals 1 minus the probability that X is less than or equal to 0. But look, it's not going to be less than 0, it's just going to be equal to 0, right? And I guess I could do a binomial probability with X being 0, or I could just say, what's the complement of this? The complement of at least 1 means 0. Well, what's the probability that 0 out of 20 donors would be O negative? It would be 0.94 to the 20th power. So, since that's the probability of nobody being O negative, 1 minus that is going to be the probability of somebody being O negative. And so I'm just going to do 1 minus 0.94 to the 20th power, and that gets me 0.71. Okay? I really could have done the binomial distribution where X equals 0, but if you know what a binomial distribution is, that really should be easy. Okay, now, this time we have a 200 donor pool, so N is 200. And so X is binomial, with N being 200, and P is 06. And I want to know the probability that at least 6 of the donors, so probably that X is 6 or more. Well, that's going to be 1 minus the probability that X is at most 5. Okay? And, well, so I'm going to say second distribution down to my binomial PDF. No, sorry, binomial CDF, because I want less than or equal to. So binomial CDF, N is 200, P is 0.06, and I want to know the probability that it's less than or equal to 5. So I say 5, and I get 0.0177. But what I really want is I want 1 minus that. So I'm going to say 1 minus answer, and that gets me 98%. So 98.2%. So if I get 200 people, I can be pretty darn confident that at least 6 of them is going to be type O negative. Okay? All right, last question of the last question. Suppose 20 donors come to the blood drive. What are the mean and standard deviation of the number of universal donors among them? Okay. Oh, come on. I wanted something hard. My mean is n times p. My variance is n times p times q. That means my standard deviation is the square root of n times p times q. What's n? 20. What's p? It's still 0.06. So this is going to be 20 times 0.06, which is 1.2. I would expect 1.2 people to be a universal donor. Okay? NPQ is 20 times 0.06 times 0.94, which comes out to be 1.128. That's my variance. So the standard deviation is simply the square root of 1.128, and that's about 1.062. So that's our standard deviation. All right? Hopefully by now this is starting to make some sense, and it's starting to feel a little bit natural for you.